Howdy, howdy, this is Mr. Potter. Today in our pre-calculus class, we're going to be talking about domain and range, which are important concepts because they tell us where a graph is and where a graph isn't. So first thing I want to do is introduce the idea of domain and range. So we're going to come up with some descriptions of what we got here. So for a relation, the domain is the set of values that may be evaluated, or you can think of that as being inputted into the relation. In other words, if I were to have some relation like f of x equals 3x plus 6. The domain is going to be all of the values that are fit to put inside this variable here, whatever my independent variable is. And the range is the set of values that may be retrieved or outputted from the relation. So if you think of the function as a machine where stuff goes into the machine and then stuff comes out of the machine, my domain is all of the good stuff that's not going to break my function machine. So anything that's not going to break my function machine, that's going to be my domain. The range is all of the stuff that I could expect to come out of this function machine. So let's go through a couple of examples. So I've got a domain, and I've got different functions here, different relations, and I want to talk about what my domain and range is. Keep in mind that when I'm talking about the domain, I'm talking about all of the values that could be inputted. And whenever we're talking about ordered pairs, that first number is the number that's inputted. So 1, 2, 3, 4, and 5 is my domain. So my domain is going to be the set containing 1, 2, 3, 4, and 5. My range is all of the numbers that I get out of my relationship. So 2, 2, 4, 6, and 7. So there's only 4 different values that I can get. I can get a 2 out of it, or I can get a 4 out of it, or I can get a 6 out of it, or a 7 out of it. Because numbers can be repeated both for the domain and for the range, we usually don't repeat them when we're listing out the discrete elements of our range or the discrete elements of our domain. Just because we're saying what values can we expect out of it. I can expect a 2 out of it. There are several ways that I can get a 2 out of it, but I can expect a 2 as one of my results. So for A, that's how I would write my domain and range. For B, my domain, well, I could plug in virtually any real number in here. I could plug in 0, 1, 2. I could plug in a negative number. I can plug in a decimal or a fraction. So my domain is going to be all real numbers. I could write it like that. I could write it as an inequality from negative infinity to infinity, or I could even write it in interval notation from negative infinity to positive infinity. There's several ways to write that, and we'll go into more details in just a few minutes. For my range, though, there's no way that I could ever get a negative number out of this, because anytime that I square a real number, I'm going to get a positive number or I'm going to get 0. So my range is going to be all real y greater than or equal to 0. In other words, I can only get values for y that are non-negative. Okay. Let's take a look at C. Here f of x is equal to the square root of x minus 2. And this can pose a problem, because if I try and take the square root of a negative number, I'm going to get a number that's not real. I'm going to get a complex number or an imaginary number. So the restrictions that I have here is that x minus 2 must be greater than or equal to 0. In other words, x must be greater than or equal to 2. And so that's what my domain ends up being. My domain ends up being that x must be greater than or equal to 2. And that restriction is because I can't take the square root of a negative number and expect a real number out of it. Now, if you're familiar with when we were talking about parent functions, this is really the square root of x function just translated 2 units to the right. And my graph, remember, looks like this normally. It starts at 0 and it is an increasing function. It's never negative. It's going to slowly rise up. Whenever I take the square root of something, I'm not going to get a negative number out of it. So for my range is going to be y greater than or equal to 0. And again, I could be equal to 0 because the point 2, 0 is on this function. Finally, when I'm looking at y equals 1 over x plus 3, I run into the problem that I can't divide by 0. Dividing by 0 gives me something that's undefined, or in some cases indeterminate. So I want to avoid that situation. So I want to find out where x plus 3 is not equal to 0, and that happens where x is not equal to negative 3. And so my domain is going to be where x is not equal to negative 3. Now for my range, the problem that I have whenever I'm dividing, if I would take a look at my parent function for 1 over x, my graph actually ends up looking something like this for the first quadrant, and then a graph in the third quadrant. But what I notice for my y values is that my y value can never be 0. I can get as close as I want to 0, but I can't actually do a division of any variable down here and ever have this be equal to 0. That's never going to work out. And so my range is going to be that y is not equal to 0. And so what we've seen here is we've seen several cases where I can explicitly list all of the elements, or I can give a inequality, or I can give an interval, or I can give a domain and range with exclusivity. Because I can either explicitly tell you what's in there, I can tell you what's not in there, or I can give inequalities or intervals to kind of tell you the range of values that are acceptable. And so what happens is we have to figure out, okay, what different things can actually affect the domain. And a couple of things that we saw that dividing by 0 is one of the problems, because we're not allowed to divide by 0. So what I essentially want to do is I want to set my denominator equal to 0, and these are bad points. This is where we're going to be using that exclusivity. So in other words, this is where I'm going to say x is not equal to some number. The other thing that can affect a domain is I can take the square root of something that's negative. And so what I want is I want this, whatever the argument is inside the square root, I want this to be greater than or equal to 0. So this often works better with interval or inequalities. Now keep in mind that I could have 1 over the square root of something. And if I had 1 over the square root of something, then I don't have this, my argument would have to just be strictly greater than 0. I'm not going to have this equality part of it, because the equality part would actually violate dividing by 0 up here. Now there is one other case that we should consider. And the other case that we really need to consider is that if there's a natural restriction by the nature of the problem. And what I mean by that is if I was to look at the graph y equals x squared. Well, y equals x squared, my domain is going to be all real numbers, and my range is just going to be where y is strictly greater than or equal to 0. But if I was to look at the area of a square, here I have a natural domain that x has to be greater than 0, because we never deal in geometry with squares that have negative or 0 length sides. So I have a domain that's affected by a natural restriction. The domain's affected by the fact that we're dealing with a specific situation, a specific word problem. And so when I'm considering my domain, I need to consider dividing by 0, I need to consider taking the square root of a negative number, but I also need to consider natural restrictions, things that the word problem contributes. So if I'm told that there's a maximum population of 1 million people, that's obviously going to affect my problem in some way. So my model, whatever function I'm using to model, I can't just let it run away and have an infinite boundary. So, with that being said, let's talk about the different notation styles. So there are several ways that we would look at inequalities. One of the ways that I would just say is that x is greater than a. So this is one way that we could see it written out verbally. Now, remember that we talked about how we have interval notation, and we also have inequalities. So if I'm dealing with interval notation, if x is greater than a, then I'm going to have a lowest possible bound of a, and we use the parentheses to show that we never actually approach that value. Notice that we're just greater than a. And there is no upper bound, so we'd use the infinity symbol. And again, because we can never reach infinity, we use the parentheses for that. We're going to use parentheses whenever we can't reach. And we're going to use brackets when we can reach. So it's the same distinction if I'm using less than or greater than versus less than or equal to, or greater than or equal to. So here I would have to say that x lies between a and infinity, but we rarely write that. Sometimes we'll just write a is less than x. Either of those are perfectly fine. And then we have graphical. And there's a couple of ways to do graphical. If I'm thinking of a number line, I'm going to have some value a, and I'm going to have a circle at a, and all the values to the right of a shaded. So you may remember these from your algebra classes, but of course we have x is greater than a. We also have, let me do this in a slightly different color, x is greater than or equal to a. And so this is where I would use the squared off bracket on a, but again, infinity can go on. My interval notation, I'm going to use the less than or equal to. And on my number line, I'm actually going to use a completely filled in dot for a, shading in the appropriate direction. So we have restrictions for this, and sometimes it's helpful just to see these written out. This is similar to our rule of 4 that we talked about. So we have a verbal description, we have a graphical description, and then we have some algebraic descriptions here. Now I can do the same idea here and say x is less than a, or b. Let me use b here. I'm going to try and use b as a lower bound and a as an upper bound. So here, I know that b is the biggest it can be, but it could go down to negative infinity. So I would have negative infinity less than x less than b. Or on my number line, I have b as a lower bound, and it's a lower bound that I can never reach. Similarly, I can talk about how x is less than or equal to b. So this is where I would have my negative infinity to be using the squared bracket, and go from negative infinity less than x less than or equal to b. And of course this is where I would have the completely filled in dot for b on my number line. Again, shading appropriately. And then, of course, I can have combinations of these. So I could have something like x is, gadzooks, this is not working well. X is strictly between, let me clear some of this up. I've got a problem here, it's just taking, there's too much writing on here, it gets a bit hassle. So let's go ahead and clear this up and then we'll continue going on here. We have combinations that we could talk about. So we can talk about how x is strictly between a and b. So here I'm going to have a is less than x is less than b, or open interval a to b. Or on my number line, I can have a, b, circles, and shading the values in between. Or I could have, I could have several ways to list this out. It's just something to be aware of, that we often will be using either inequalities or intervals or graphical. All of these are valid ways to denote domain and range. So something that we really should keep an eye on is that in general, functions with a restricted domain will have a restricted range. So for example, if I were to have y equals 1 over x, this has a restricted domain. X can't be equal to 0 because I can't divide by 0. And so my range also ends up being restricted. Y can't be equal to 0. If I'm looking at y equals the square root of x, then my domain is that x must be greater than or equal to 0, because I can't take the square root of a negative number. My range is similarly affected. My graph can never be negative. The y value can never be negative. And then we also have this idea of odd functions and even functions. Keep in mind that even functions, remember, even functions tend to have that y-axis symmetry. And if we have y-axis symmetry, then we're very rarely going to extend from negative infinity to positive infinity on the y-axis. So even functions will often have a restricted range. Odd functions will often have unrestricted range. Now, I say often because there are functions like this function here, which is an odd function, but it does have a restricted range. But it's often nice to think of, if I'm looking for a function that has an unrestricted range, I'm going to be looking at odd functions primarily. Similarly, even functions will have restricted ranges, but later on in this course, we'll actually be talking about some even functions that have an unrestricted range. So it's not a universal thing, but it is often something that's good to take a look at. So it's just something to consider. It's a good rule of thumb. It's not an absolute, though. All right, so I want to go through some examples here. So first thing I want to do is I want to find the domain of range of this function. I've got f of x equals x squared minus 3. Now, normally when I'm thinking of a function, I often want to think of the parent function, which we talked about in our previous video. So y equals x squared, if I take a look at this graph, one of the things that I notice is that, one, this graph goes forever to the left. That's what this arrow is kind of saying, and forever to the right. But this is an even function. I do have that y-axis symmetry, so it looks like I have a restricted range, and my range never goes below 0. Now, the difference between this function and the function that we're trying to analyzing is that this is just basically shifted over a certain number of units. But if I take this graph and shift it over 3 units, I'm still going forever to the left, and I'm still going forever to the right. So my domain is going to be all real x, or from negative infinity to infinity, or negative infinity is less than x is less than infinity. Or if I was to do this on a number line, I would just end up shading everything. For my range, though, my range is going to be y greater than or equal to 0. In other words, going from 0 to infinity, or y lying strictly between 0 and infinity, possibly equal to 0. And on a number line, then I'm going to have 0 here. I'm going to be bounded by this, so either a bracket or a dot, and I'm going to be shading everything to the right. And something that's nice to know is that polynomials have unrestricted domains. Polynomials are always going to be of the form a times x to the n plus b times x to the p plus c times x to the q plus dot dot dot. But the thing is, raising a number to a power is not one of the restrictions that we talked about. It's not dividing by 0, it's not taking the square root of a negative number. And if I'm dealing with a polynomial situation in a purely algebraic environment, this is not something where I'm going to have a natural restriction either. So whenever I'm dealing with polynomials, this is always going to be the result. I'm always going to have all real numbers being my domain. Now, my restrictions may happen on my range just because we're dealing with the idea of even versus odd. But in general, if I'm dealing with a polynomial, odds, so odd degree polynomials, are going to have unrestricted range. So if I think about y equals x, my graph of y equals x is a straight line that goes forever up and forever down. If I think of y equals x cubed, then I'm going to have a graph that does something like this and then like this as well. But again, forever up and forever down. My even polynomials are always going to have some hump in here along the way that's going to keep me from going forever in one direction. All right, so looking at this problem, there are two things that we notice. One is that dividing by 0 is going to be an issue. And two, taking the square root of a negative number is going to be an issue. All of these are going to give me bad points. So I need to look at this expression, and I want to know, when is this expression equal to 0? Because this is going to be a problem for me. So looking at where this is equal to 0, I'm going to have to factor this, and luckily this factors out nicely. So I end up with x equals 1 or x equals 2. Now keep in mind that these are bad points. And so these are going to affect my domain in this way. I can't divide by 0, so they're going to be bad points for that nature. But I also need to consider these values here. In other words, I need to look at x squared minus 3x plus 2 and find out where it is less than 0 as well, because those are going to be bad points as well. So if I were to look at a number line and evaluate these points for x squared minus 3x plus 2, okay, well, here's 1, here's 2, and I've got 3 ranges that I need to consider. Now, the thing is, what's nice about being equal to 0 is that's where I change from negative to positive, or where I change from positive to negative. So if I change sign here, all of these numbers have to be the same. I can choose any representative, like 0, and see what it does. Well, 0 minus 1 is negative 1. 0 minus 2 is negative 2. And negative 1 times negative 2 gives me a positive, which means if I have 0 being positive, every number in this interval has to be positive, And so it's going to have to be part of my domain. So from negative infinity to 0, not including, excuse me, not 0, 1. Not including 1, because 1 is a bad point. Now I need to consider this interval from 1 to 2, so let me try 1.5. So 1.5 minus 1, that's positive 0.5. 1.5 minus 2 is a negative 0.5, and a positive times a negative is a negative, which means these are going to be bad points. Now I need to consider what happens from 2 on, so choosing a representative 3. 3 minus 1 is 2, positive. 3 minus 2 is positive 1, and a positive times a positive is a positive. So anything from 3 on is going to be a good point. And so my domain ends up being this situation. Now, when I want to consider my range, I need to consider the y values. Well, I know that a fraction can never be equal to 0, so y can't be equal to 0. This is a polynomial. And so what's happening here is that for these values in this range, because this is positive, I know that the square root of that is going to be positive. So I know that I'm positive on this domain. Similarly, because this expression is positive, the square root is also going to be positive. So I know that I'm positive on this domain. So it's not just that y is not equal to 0, but y is strictly greater than 0. So in other words, my interval would be from 0 to infinity. So just keep in mind that when we're talking about the domain, domain's really easy to do algebraically, but the range can take a little bit more thought. Oftentimes, though, you can just do the thought, just kind of knowing about how parent functions behave. So here, the main parent functions I'm looking at is the 1 over x parent function and the x squared parent function. 1 over x has the graph that looks kind of like this. And this function is how I knew that y could not be equal to 0. With this x squared, I have a parabola. And I know because my lead coefficient is positive, this parabola is just being shifted up or down, shifted left or right. But the thing is, I'm only going to be concerned about the positive values because what's inside the square root cannot be negative. That's how I was able to restrict myself, by doing a combination of these two ranges. All right, the last experiment that I want to do are these graphs here. So I want to find the domain and range of these graphs. So keep in mind, domain are the x values. So this graph on the left starts here and keeps going until it stops here. So I'm starting at -2, and I'm continuing on until I reach a +3. So my domain I could think of as going from -2 to +3. And I actually do hit these values. Notice I've got dots there. So these are actual values that I can be equal to. For my range, I want to consider my high point and my low point. This is the highest point on the graph. This is the lowest point on the graph. So I'm going from a -1 to a +4. So my range is going to go from -1 to +4. And so I can just look at my graph and look at how high and how low my graph is to figure out my range, how far to the left and how far to the right to get my domain. For this second problem, my graph starts here and it gets closer and closer and closer and closer, but it never actually reaches here. It just gets really close to that point. So my domain is going to start at -1, and we do actually hit that point. But we get closer and closer to x equals 2, and that's an asymptote that we never quite reach. So my domain is going to go from -1 to +2. For my range, I'm looking at my high point and my low point. But the thing is, because of this arrow on my graph, my low point is actually -infinity. So my range is going to go from negative infinity all the way up to positive 1. And again, we never use a bracket for infinity. We always use parentheses. But because we can hit that 1 is going to be equality. Finally, looking at our third graph over here, I'm looking at the left end, which is here, but again, it's a hole. I never actually hit that point. And we're going to keep on going to the right until we hit this point here, and because this is a dot, we actually do hit this point. So my domain is going to go from negative 2, which is going to be an open interval, it's parentheses, to a positive 3, and because I do hit that positive 3, I am going to use a bracket. For my range, again, I'm looking at how low does my graph go and how high does my graph go. And I notice a couple of things. One is I have a hole here, but I have a dot here. And so because I have a dot here, I actually do hit this point. It's not going to be in a parentheses, it's going to be a bracket. So my range is going to go from negative 3, and including that point, all the way up to positive 2, including that point. Understanding domain, understanding range is very important for us to understand the nature of functions and relations. Understanding the nature of graphs allows us to predict the behavior and understand what's going on in our simulation, in our example, in our model. Once again, this is Mr. Potter. Thank you for watching. Have a great day.